Welcome. Today we're diving into the fascinating world of probability and markets. Whether you're working in finance, making decisions in daily life, or just curious about how uncertainty shapes our world, an intuitive grasp of probability is invaluable. These concepts might not feel natural at first, but with a bit of familiarity, they become powerful tools for reasoning. Let's start our journey by understanding why probability is so important, not just for professionals, but for anyone who wants to make better decisions in uncertain situations. Randomness is everywhere, especially in financial markets where prices fluctuate unpredictably. But randomness isn't just about chaos, it's about uncertainty and how we reason through it. Think about rolling a die. Each outcome seems objectively random, and we can agree on the likelihood of each side showing up. Now consider predicting tomorrow's weather. Even with lots of data, there are so many factors at play that no one can be certain. Sometimes, events feel random simply because we lack information, even if the outcome has already happened. In all these cases, probability helps us make sense of uncertainty. Randomness comes in different forms. There's binary randomness, like whether it will rain tomorrow, yes or no. Then there's discrete randomness, such as rolling a die where the outcome is one of a finite set of possibilities. Finally, there's continuous randomness, like tomorrow's temperature, which could be any value within a range. While these categories might feel distinct, they're actually quite similar in how we analyze them. The key is recognizing that, in many cases, randomness is just a reflection of what we don't know yet. In dealing with random events, counting possible outcomes is often the first step. If each outcome is equally likely, probability becomes a simple matter of counting. For example, with a standard six-sided die, the probability of rolling a 1 is just 1 out of 6. If you want to know the chance of rolling a prime number, you count how many sides are prime and divide by 6. Sometimes things get trickier, like when rolling two dice and adding their results. Not all sums are equally likely, so careful counting is essential to get the right answer. Make things precise, we use notation like p-outcome to represent the probability of a specific event. This is a function that takes an outcome and returns a number between 0 and 1, showing how likely it is. For example, p-roll is 1 equals 1 6. If you're interested in more complex events like rolling a prime number, you sum the probabilities of each relevant outcome. This notation helps us move from intuition to mathematical formulas, making it easier to solve more challenging problems. Not all events are equally likely. Sometimes you might have a situation where certain outcomes are more probable than others. For example, if something has a 30% chance to be 0, 20% chance to be 1, and 50% chance to be 2, you can imagine 10 equally likely events, with 3 resulting in 0, 2 and 1, and 5 and 2. This trick helps you visualize and calculate probabilities even when the chances aren't the same for each outcome. Probability is all about assigning numbers to possible outcomes. Each outcome gets a probability greater than or equal to 0, and the total probability across all outcomes must add up to 1. If something is certain to happen, its probability is 1. These rules help us keep our calculations consistent and ensure we're considering all possible scenarios. When dealing with sets of outcomes, we simply add up the probabilities of each outcome in the set. And diagrams are a great way to visualize how probabilities of different events relate. For example, the probability of A or B happening is the sum of their individual probabilities minus the probability they both happen. Similarly, the probability of not A is just 1 minus the probability of A. These set operations make it easier to handle overlapping events and ensure we don't double count any possibilities. Dependence is a crucial concept in probability. When two events are independent, the outcome of one doesn't affect the other. For example, flipping a coin and rolling a die are independent events. The probability of both happening is just the product of their individual probabilities. This property makes calculations much simpler, especially when dealing with large sets of unrelated events. Let's look at rolling two dice. Each die is independent, so the probability of rolling a specific number on each is just 1 6. The probability of rolling a 1 on both dice is 1 6 times 1 6, or 136. This extends to more complex combinations, like rolling even on the first die and odd on the second. Independence allows us to break down big problems into manageable pieces. Drawing cards from a deck is a classic example of independence. If you draw a card and put it back before drawing again, each draw is independent. But if you don't replace the card, the probabilities change because the deck has fewer cards. Understanding whether events are independent or not is key to setting up the right calculations in probability problems. Random variable is a way to assign numbers to outcomes. For example, the number of pips on a die roll or the price of a stock in the future. Each possible outcome has a probability, and together these form the distribution of the random variable. Some distributions, like the uniform distribution, are common. Every outcome is equally likely. Others, like the sum of two dice, are not uniform. Random variables help us translate real-world uncertainty into numbers we can analyze. Uniform distributions mean every outcome is equally likely, like rolling a single die. But when you add two dice together, some sums are more likely than others. For instance, there are more ways to roll a 7 than a 2 or 12. Recognizing whether a random variable is uniform or not helps you choose the right approach for calculating probabilities and expected values. You can create new random variables from existing ones. For example, if you roll two dice, you might look at their sum or their product. Or if you have the temperature in Fahrenheit, you can convert it to Celsius using a formula. This flexibility lets you model a wide range of real-world scenarios, from games to financial outcomes. Expected value is the average outcome you'd expect if you repeated an experiment many times. For a die, it's the sum of each possible value times its probability. For a standard six-sided die, the expected value is 3.5. This single number gives you a sense of the center of the distribution and is one of the most useful tools in probability. Calculate expected value, multiply each outcome by its probability and add them up. For example, with a die you do 1 times 1 6 plus 2 times 1 6 and so on up to 6 times 1 6. The result, 3.5, is the average you'd expect over many rolls. This method works for any random variable, no matter how complex the distribution. Expected value has some very useful properties. For two random variables x and y, the expected value of their sum is just the sum of their expected values even if they're not independent. If they are independent, the expected value of their product is the product of their expected values. These properties make calculations much easier and are widely used in both probability theory and real-world applications. Indicator function is a clever way to simplify calculations. It assigns 1 if an event happens and if it doesn't. The expected value of an indicator function is just the probability of the event. This is especially useful in betting scenarios where payouts depend on whether a certain event occurs. By using indicator functions, you can quickly calculate expected payouts and make better decisions. Law of large numbers states that as you repeat an experiment more and more times, the average result will get closer to the expected value. This is why casinos and insurance companies rely on probability. They know that over time the actual outcomes will match the averages predicted by probability theory. It's a powerful concept that underpins much of modern finance and statistics. Sometimes knowing just the expected value isn't enough. You might want to know how much the outcomes can vary. Confidence intervals give you a range where you expect most outcomes to fall. For example, a 90% confidence interval for a random number between 0 and 100 could be 0, 90, or 191. These intervals help you understand the risk and variability in uncertain situations. There are several ways to measure how much a random variable can deviate from its expected value. You can look at the minimum and maximum, calculate the average deviation, or use squared differences. These measures help you quantify risk and make more informed decisions, especially when large losses are possible. People often overestimate their ability to predict outcomes. For example, if you give a bunch of 95% confidence intervals, fewer than 95% might actually contain the true result. It's important to be aware of this tendency and adjust your estimates accordingly. Practicing with real data and checking your intervals can help you become more accurate over time. Conditional probability is about updating your beliefs as you learn new information. For example, if you think the weather in London is 60 degrees but then learn it's snowing, you'll adjust your estimate downward. The probability of an event, given that another event has occurred, is called conditional probability. This concept is fundamental in both probability theory and real-world decision-making. Formula for conditional probability is straightforward. P of B equals PA and B divided by PB. This tells you the probability of a happening given that B has already happened. For example, if you roll a die and know the result is at least 4, the probability of rolling a 5 is now 1/3, not 1/6. Conditional probability helps you refine your predictions as you gather more information. Venn diagrams are a helpful way to visualize conditional probability. The overlap between two sets represents the probability of both events happening. By dividing the overlap by the total probability of the given condition, you can see how the formula P of B equals PA and B/PB works in practice. This visual approach makes it easier to understand and apply conditional probability. Let's apply conditional probability to a real example. If you flip 3 coins, what's the probability of getting exactly 2 heads given that you get at least 1 tail? First, count the outcomes that satisfy both conditions, then divide by the total number of outcomes with at least 1 tail. This process helps you break down complex problems into manageable steps. Conditional probability isn't just for math problems, it's a constant theme in trading and markets. When you make a trade, you update your beliefs based on new information, just like adjusting your estimate of the weather when you hear it's snowing. This mindset helps traders react quickly and make better decisions as market conditions change. Trading has its own language. When you want to buy, you place a bid. When you want to sell, you make an offer. You specify the price and quantity, and your order stays active until it's filled or you cancel it. If someone trades against your order, it's called a fill. Understanding this jargon is essential for navigating financial markets and making informed trades. In making a market, you might be willing to buy and sell at different prices. For example, you could say, I'm too bid for 10, meaning you want to buy 10 units at $2 each. Or I have 10 at 4, meaning you're selling 10 units at $4 each. If you're willing to do both, you might say, I'm 2 at 4, 10 up. This shorthand helps traders communicate efficiently and make deals quickly. If someone trades against your order, it's called a fill. If your entire order is filled, it's gone from the market. If only part is filled, the rest remains available. You can also specify partial trades, like buying or selling only a portion of the available quantity. These mechanics are fundamental to how markets operate and ensure flexibility for all participants. Key trading strategy is to buy below the expected value and sell above it. For example, if a contract pays out based on a die roll and the expected value is $3.05, you want to buy for less and sell for more. This approach helps you make profitable trades over time as long as you're careful about the risks involved. Risk management is crucial in trading. Even if the expected value is positive, you can still lose money in the short term. For example, buying a contract for $3.05 that pays out $1 means a $2.05 loss, which happens 1/6 of the time. Potential losses are large relative to your capital. You need to adjust your strategy to avoid running out of money when better opportunities arise. In trading, you want to balance the likelihood of making a trade with the potential profit. If you bid too low, no one will sell to you. If you bid too high, you might not make any profit. Finding the right balance is key to successful trading, and it often involves a mix of probability, expected value, and market intuition. Let's look at some practical market scenarios. What's the value of a contract based on a 20-sided die roll, or the maximum of 3 6-sided dice, or a contract where you can reroll a die once if you don't like the first result? Each scenario requires careful calculation of probabilities and expected values, as well as consideration of who gets to make decisions and how that affects outcomes. Imagine a contract that pays 1 million times the outcome of a die roll. The stakes are huge, and a bad outcome could be devastating. In these situations, it's even more important to understand the risks and adjust your strategy accordingly. High-stakes trading requires discipline, careful calculation, and a willingness to walk away if the odds aren't in your favor. Adverse selection is the idea that the trades you get to make are often worse than they appear, because someone else is choosing to trade against you. If you're trading with someone who's just as skilled, you need to be extra careful. There's a good chance you miss something. Understanding why the other person is trading helps you avoid costly mistakes and make better decisions. When someone trades against your order, that's new information. You should update your beliefs about the value of the security. If you bought and someone sold to you, maybe the true value is a bit lower than you thought. This process of updating beliefs is closely tied to conditional probability and is a key part of successful trading. Groucho Marx once said, "I don't want to belong to any club that will accept me as a member." This witty remark captures the essence of adverse selection. If someone is eager to trade with you, it's worth asking why. Maybe they know something you don't. Always be cautious and consider what the other side might know before making a trade. Recursion is a powerful tool for solving probability problems, especially those involving repeated actions. For example, if you flip a coin until you get heads, you can set up a recursive equation to find the expected number of flips. This approach breaks down complex problems into simpler, repeatable steps, making them easier to solve. Some processes like flipping a coin are memoryless. The probability of success doesn't depend on past outcomes. This property makes recursive solutions especially effective. For example, the expected number of flips to get heads is always the same, no matter how many tails you've already seen. Recognizing memoryless processes helps you set up and solve recursive equations efficiently. Solve a recursive equation. Start by expressing the expected value in terms of itself. For example, the expected number of flips to get heads is 1 plus half the expected value if you get tails and have to start over. Solving this equation gives you the answer. This method is widely used in probability, especially for games and processes that repeat until a certain condition is met. In generalizing a solution, it's important to check edge cases. Try plugging in extreme values like 0, 1, or infinity to see if your formula still makes sense. This practice helps catch errors and can provide insights into how to simplify or improve your solution. Small cases are especially helpful for understanding complex problems. If you're stuck on a big problem, try simplifying it by considering a smaller version. For example, if you're struggling with a game involving 100 players, start with just 2 players and see how the solution changes as you add more. This approach can reveal patterns and make it easier to generalize your solution to larger cases. Many people believe you need to be a mental math wizard to succeed in interviews, especially in finance. While numeracy helps, what matters more is your ability to reason through problems and check if your answers make sense. Quick calculations are useful, but thoughtful problem solving is even more important. Another myth is that you need to know advanced math to do well in interviews. In reality, most questions are designed to be solved with creative reasoning and intuition, not obscure theorems. Simple, intuitive answers are often preferred over complex solutions. Focus on understanding the problem and explaining your thought process clearly. It's a common misconception that getting the wrong answer means you fail an interview. In reality, interviewers care more about how you approach tough problems, how you respond to hints, and how you handle being wrong. Collaboration and clear communication are valued just as much as the final answer. You might have heard that you need to act a certain way in interviews, super confident, fast, or assertive, but the truth is, interviewers want you to be yourself. It's okay to take your time, admit uncertainty, and ask for clarification. Authenticity and thoughtful answers are always appreciated. Remember, your interviewers have been through the same process and understand the challenges. They're looking for candidates who can think clearly, communicate well, and handle uncertainty with grace. So relax, focus on your reasoning, and don't be afraid to show your thought process. Good luck.